Yes. Hello dear students, as you know, myself Mahesh Prasad from Department of Physics. Yes, we have already started up with a chapter called as Mechanical Properties of Solid, right? Yeah. So in the previous class we have discussed about what? Regarding different types of stress we have studied, correct? Like we have studied normal stress and we have studied volume stress, as well as we have studied about shearing stress, correct? And normal stress, again it is going to split as what exactly? That is the two types. If length is going to increase, we can have a tensile stress. If the length is going to decrease after applying a deforming force, I can call it as compressive stress, correct? Now the thing is, at the meantime, our job is to learn about the kind of strain which you can see over here. So what do you mean by strain over here, by the way? Strain is nothing but, so basically we have three type of strain over here. So strain in the sense what actually, so whenever you are applying something, for example, if I take one object somewhat like this, and if I apply a force like a deforming force to, what do you mean by deforming force, by the way? The force which is responsible for deformation, correct? So if it is so, don't you think its length is going to vary? So when a length of the particular object is going to vary with respect to its initial object, then the ratio of change in object with respect to, or a change in dimension with respect to original dimension, I can say it is a strain. So what is the strain I can have? Basically, the strain which gives what? It is equal to change in, that is the change in dimension. The change in dimension to the original dimension is called as what? Strain over here. Okay, so always remember this. So as you know, we can classify into the three different types. The one is the longitudinal stress. The first one we can deal it as a longitudinal strain, and this is also called it as a normal strain. That is normal strain over here. Nothing but the same. In examination, if they ask to define normal strain or a longitudinal strain, that is nothing but the same over here. Okay, don't get confused. In the sense, you are supposed to apply a deforming force normal with respect to its area of cross section. For example, if this is the length, and here, for example, if I take it as a length somewhat like this, for example, this as a conductor, don't you think it is having some area of cross section over here? Correct? Correct, right? Yeah. So for example, the length of the wire, if I take it as a L over here, what do you mean by L over here? Length of the wire or length of a conductor. Okay. Now I have applied the force in such a way that it is going to take an extension over here. So if I take extension, don't you think the corresponding length is going to increase with respect to somewhat like this? And this is a change in length as delta L over here. Okay, which is nothing but increasing in length. So initially it was a length as L, and after applying a deforming force, it has increased its length as a d delta L over here. What about delta L which is over here? It is nothing but increasing length. So if it is an increasing length, what happens here? We can call it as a tensile stress, correct? No? So if you apply normal with respect to, for example, if it is the area of cross section, and if you apply the force in this direction, which is nothing but normal with respect to its area of cross section, I can have, correct, right? Yes. So similarly, so how to get a formula with respect to longitudinal strain or a normal strain over here? It is very simple. I can have that is a longitudinal strain which is equal to I can have change in length, that is the change in length divided by original length. What is the change in length I can have over here? What is the change in length I can have? That is the longitudinal strain which is equal to delta L by L over here, and this is the formula I can have for normal strain or longitudinal strain over here. Okay. So do you think what is the SI unit of longitudinal strain I can have over here? Think and give me the answer, or think yourself. So delta L, what is the SI unit of delta L in the sense? It is also kind of length, right? And what about this original length in terms of meter? So if I say SI units, see, meter by meter, which is equal to 1, so which means it is SI unit I can have, it is a dimensionless quantity, it is dimensionless quantity. Okay, and we have discussed in the first chapter as well, whenever we are discussing about the units and measurement, at that time I have given one example that where strain is a unitless quantity. Why? Because of this. Because strain is nothing but what? Or longitudinal strain is nothing but what? It is a change in length with respect to original length. Its unit is going to get cancelled out because the numerator we have meter, denominator as well as we have a meter over here. Correct? Yes. And this is all about the longitudinal or normal strain. And similarly, we can have the one more strain, that is volume strain. That is a volume strain over here. This volume strain is also called as a bulk strain. That is called as bulk strain. Okay, bulk strain. What do you mean by bulk as well as volume? So you take one sphere somewhat like this, somewhat like this one. Okay, you take one sphere, and what happens here? So when I put the same sphere into the water, what happens? Don't you think the force which is acting by the water uniformly on the surface of a sphere over here? So which means it is a deforming force which is acting or restoring force per unit area, which is nothing but when it is going to act restoring force per unit area, when the force which is applied uniformly on the surface. If the force is acting uniformly on the surface, what happens? Don't you think its volume is going to decrease over here? So similarly, I can have the decreasing volume. It looks somewhat like this. Which means, if I say initial volume of the sphere, if I say as V, what is this V I can have? That is nothing but delta V, which is nothing but a change in volume. Do you think its shape changes? No. Whenever we have a uniform force which is acting on any surface, its volume is going to decrease, not its shape over here. Okay, keep that in your mind. So what is the formula I can have with respect to your volume strain over here? That is very simple. I can have like that is the volume strain. The volume strain is equal to the change in volume. That is the change in volume divided by original volume. That is the original volume. So what is the change in volume? I can say that is the volume strain is equal to, what is the change in volume I can have over here? What is the change in volume? That is the delta V, because it is shrink over here. That is delta V divided by letter V over here, because V is the initial volume of a sphere over here, whereas the delta V I can call it as it is the change in volume. And one more thing you have to remember, one minus symbol should come over here. Similarly, I can why? Because if dimension is decreases with respect to its initial dimension, and this is an indication of a minus symbol over here. Similarly, in this case as well, if I apply a compressive stress, like if I take the same object and if I compress by applying a force as a compressive force, so what happens? Decreasing length will take place, right? So in that particular process, I can put minus sign over here. So what figure is shown over here, there is nothing but increasing length. If you have increasing length, no need to put negative sign over here. And since here the volume is going to decrease, in the sense the dimension of volume is decreased with respect to its initial volume, correct? No? So that's why this minus, which indicates decreasing volume, which means negative indicates decreasing dimension. Okay, This is how exactly it works over here. And one more thing I can have, that is the shearing strain and shearing. That is the shearing strain. And shearing strain is also called as a tangential strain. That is the tangential strain. Why it is a tangential strain? Because we are supposed to apply a force tangentially on the surface, right? And in the sense, if you take one object somewhat like this, if you take one rectangular object, if I take, for time being I'll take this as having height as h, and it is having the length over here as L over here, okay, for time being. Now, if I apply a tangential force, in the sense, tangentially on the surface, okay, so in the sense, I am applying a force over here, so that it takes a deviation somewhat like this, and this dotted line which indicates what, and this was the initial dimension, and there is the angle theta comes into a picture over here, correct? No? So this is a position which is changed with respect to what, its initial or fixed point over here, correct? Yeah. So this is called as delta L over here. Delta L which represent what? Relative displacement. This is the relative displacement with respect to its fixed position. What was the fixed position? Over here. So initially it was, it was like, yeah. So initially it was, that is the fixed point somewhat like this. And when I apply tangentially, what happens? It is going to shift somewhat like this. So there is an angle between these will comes into the picture. So that's why here, how to define your shearing stress or shearing strain over here? So it's very simple. With respect to angle, I can have if I take tan theta, if I take tan theta or tan function, because opposite as well as adjacent will comes into the picture. That's why. So what I can have, that is delta L divided by h I can have. Where delta L deals with what? It is the relative displacement with respect to a fixed point. With respect to fixed point, or it is a ratio of the relative displacement with respect to fixed point to the height of the object. Where h deals with what? Height over here. Where delta L deals with what? It is just a relative displacement. Are you getting? Yeah. So since this angle is very small, right? Yeah. So I can have theta which is equal to delta L by h, and this is the formula I can have over here. Okay, and this is the volume strain, and this is the longitudinal strain. Okay, so this is a way of getting your tangential strain over here. So initially we have started up with the topic called as longitudinal strain. Longitudinal strain, how we are supposed to apply your stress over here. You are supposed to apply how? Normal to the particular surface. So that if the change in dimension, if it is increases, you can take a positive over here. If you apply compressive stress, if the dimension is going to decrease, well, you have to put one negative symbol over here. Whereas negative symbol which indicates what? It is what? It is decrease in dimension. Are you getting? Yeah. So similarly, I can have volume strain. Volume strain in the sense when I can have a uniform force which can be applicable or can be applied on the throughout the surface just by take your ball and dip into the water over there. So that what happens? The force which is exerted by the water acting uniformly on the surface. Okay. So that what happens? Its dimension is going to decrease. So if dimension is going to decrease, and your job is to put one negative symbol. Okay? Yes. So, and one more thing we have studied about tangential strain or a shearing strain over here. Similarly, and since the name itself deals, that is a tangential, in the sense you are supposed to apply a force tangentially on the surface, and this is how exactly it works. So, if you apply tangentially, what happens? Theta comes into a picture. Okay, so if we have a theta, you can go with the tan function over here. So I can write tan theta is equal to delta L divided by h, where theta is equal to delta L divided by h. Okay, so this is what exactly we can have under the concept of strain over here. Okay. Yeah. And we'll move on to the one more topic that you can see on the board, that is Hooke's law. So this law is very simple. Like you take one object somewhat like this, spring, and you keep on load up hanger. With respect to hanger, you keep on load this. Whatever. So what are the observation you can make over here? So if I keep on increasing the load, don't you think the strain is also increases? Correct? Strain in the sense change in dimension with respect to original dimension, which means the force which is applying in terms of a load over here, which means if I keep 1 kg over here, it extended somewhat like this. If I add 1 more kg, it becomes a 2 kg, and the strain is increased one more times. Correct? No? So which means what he says that within elastic limit, stress is directly proportional to strain over here. So this is a definition which is given by Hooke, which is valid as well, in the sense he can say the stress is directly proportional to strain over here. So since we have some proportional things over here, so can I get one constant like stress which is equal to K into strain over here, where K is called as elastic constant, that is elastic constant, that is the K. So are you getting my point? So what exactly it means? So stress which is equal to or stress is proportional to strain when within a elastic limit, in the sense if I leave at this particular point, again it should come back to its initial position, again it should regain its original configuration. Are you getting? So if it is so, I can say this Hooke's law is valid. Now the thing is, one more concept we need to do, that is if I plot a graph versus stress versus strain, so what I can observe over here is that, so you take one line somewhat like this, that is the stress, and you take one more line, that is the strain over here. Okay? Okay. So now, stress, if I say in the y-axis and the strain in the x-axis. Now, you take a point O over here, you take a O over here, then you can extend, there is a rubber band in my hand, and you can extend up to certain point, right? And if you apply a larger force, the possibility of a breaking over here, the breaking of this wire will take place, or breaking of rubber will take place, correct? So now, if I extend up to point P, and this is called as point P over here. This is a point where the point P which deals with the proportional point, the proportional limit. The proportional limit. Okay, where point P which is called as proportional limit, in a sense. If I say it is this is a point where there is no force which is applied over here. Now, if I apply a force like somewhat like this, and this point is called as point P, where if I leave at this particular point, it can retrace its path. Again, it's moving towards its initial configuration. Okay, so at this particular point, the body or the particle, or at this particular point, it can retrace its original path like PO. So if I extend further force or stress over here, so what happens? It takes a little deviation somewhat like this, and this point is called as Q over here, where Q is called as elastic limit. That is called as elastic limit. That is called as elastic limit over here. Okay, this point Q is called as So, but at this particular point also, at this particular point in the sense at Q also, if I leave, it is going to retrace its original path. So it means it can retrace like QPO. But if I apply a further stress, what happens? Stress in sense forcible limit area. It can reach up to point R over here. Okay. So this point R is called as what? Yield point. Where R is called as yield point. That is called as yield point. Okay. So at this particular point, what happens? It is not going to regain its original configuration. Are you getting? So that it can have a permanent set somewhat like this. That is called as O dash. At this particular point, is there any stress? Is there any corresponding stress? No, right? So which means, though I have not applied any stress at this particular point, but the particle or that elongation will retain at this particular point over here. It is not going to regain its original configuration, which means this is called as permanent set. That is called as permanent set over here. Okay. So now, if I apply further, what happens? If I apply further, and this particular point is called as, let us say T, is called as maximum strength of the material. That is called as maximum strength over here. That is called as T. Now, if I further extend more, what happens? It is going to break. That point is called as U over here. That is U is called as fracture point. It is called as fracture point. Where U is called as what? Fracture point. What do you mean by U, by the way? Correct? Now, if you apply a more force, if you stretch more, what happens? It is going to break. So, at that particular point, by seeing this figure only, you will get to know what type of material is that. Okay? So, this is a point where it goes somewhat like this and this is end up over here. So, and the corresponding point, I can say it is T dash. That is called as the stress corresponding to the maximum strength of the object. Okay. So, this is how exactly it works over here. Now, there are two type of material comes. That is, one is ductile material and one more is brittle material. Brittle material. If you stretch more, for example, if the material which is having a more plastic deformation, in the sense, what is the plastic body? The material, it does not regain its original configuration. In the sense, if you can stretch more of a particular material, which means if the particle shows maximum plastic deformation between a point Q to point U, I can say that particular material is called as what? Ductile material. In the sense, if particle or if a body shows maximum plastic deformation between Q to U, I can call it as ductile material. Which example I can give over here? I can give example like aluminium, I can give copper. So these are the example I can give over here. Now think about a brittle material. So use your common sense if you have. So what would be the definition for a brittle material over here? It is very simple. If a body shows less or minimum plastic deformation, then I can say between where? Between point Q to point U, which means very less plastic deformation, which means the body is going to break so early. So which example I can take? Example I can take it as glass. Correct, no? In terms of glass, if you apply a small amount of force also, it is not going to take any elongation or any extension over there. It is going to break fast. You cannot extend that particular object, correct? So this is the basic idea about if you plot a graph versus stress versus strain. By looking at the graph only, you will get to know whether it is a ductile material or whether it is a brittle material. So what about a ductile material? If the body shows maximum plastic deformation between point Q to point U, I can say it is a ductile material. Which example I can give? That is a copper, like copper, aluminium. These are the example I can give under this particular concept. So what about the brittle material? The material is showing very less plastic deformation between a point Q to point U. Where point U which deals with what? Where point U which deals with what? It is just a fracture point, right? Yeah. So if the particle shows very less plastic deformation between point U to point Q, I can have that particular material which is called it as brittle material. Which example I can give? Simply I can give like a glass as an example for brittle material. Yes. Yeah. Thank you very much. We will see in the next class. Okay. Yes.